This is an isothermal expansion, this guy. So what that means is that the temperature stays the same. This is a constant temperature process. All of these points are at the same temperature, okay? What that means for you formula-wise is that, the combined gas law is PV over T equals PV over T, right? The temperature stays the same, so really we can just say PV equals PV, okay? Now, it says, how could you show this process is isothermal? Well, check out the beginning here. 6 times 2 is 12, right? I'm going to ignore the times 10 to the 5th and the whatever, right? So 6 times 2 is 12, right? Notice here we've got an intersection with a line. 4 times 3, that's also 12. Ooh, it goes through this one. That's 3 times 4. That's also 12. Look at this guy. This is 6 times 2. That's 12, right? So P times V is always the same. And I'll bet that this one is 1.5, right? Because 1.5 times 8 would also be 12, right? Okay. So it'll be 1.5 times 10 to the 5th pascals at B, right? But anyway, what is the temperature at A? How could you show this process is isothermal? Okay, so we already did this. We already did that. Just look at the PVs and show that the PVs are the same. Okay, at least for a couple spots. And this is a question you see on IB tests, right? Let's find the temperature at A, right? So PV is nRT, so therefore T is PV over nR, right? So let's see, at A, we've got the pressure, we've got the moles, so we're all set. Okay, so pressure at A, we're looking at here, is 6E5. The volume is 2E minus 3. The moles are strangely specific. And then R is 8.31. And they'll do this. IB likes to do this. They'll give you numbers where it comes out even. I mean, don't worry if it doesn't come out even. But more often than not, they tend to give you numbers that come out even. All right, so 6E5 times 2E minus 3 divided by 0.4513 divided by 8.31. And I get 319.97. So obviously I engineered these numbers to get something close to 320 kelvins. All right. So what is the pressure at B? Oh, by the way, the temperature at B is also 320 kelvins. This is 320 kelvins. That's 320. The whole line here is 320 kelvins. This is called an isotherm. All right, let's see the pressure at B. Okay, we can just do PV equals PV, right? Now you could use the ideal gas law if you want. Okay, so it's going to be, P is going to be nRT over V. You could do that. You could find the pressure at B using that. I'm going to use the combined gas law. So PV equals PV. Right, so the pressure at A is 6E5. The volume at A is 2E minus 3. All right, and then that equals the, we don't know the pressure at B, but we know the volume, right? So the pressure at B, and then our volume is 8 times 10 to the minus third. And of course, you'll see if when we do this, 6E5 times 2E minus 3 divided by 8E minus 3, and we get the pressure at B is 150,000, just like we predicted, right? This is 1.5 times 10 to the 5th, right? Okay. So we could have done that, just by inspecting. Okay, what is the temperature at B? Well, it's 320 kelvins, right? It's isothermal. Delta T is 0. Okay. Okay, the work done for this process is about 1,664 joules. Calculate the Q and the delta U. Okay, so we know that Q is delta U plus work. Now, remember that the internal energy is 3/2 nRT. If T doesn't change, then the internal energy doesn't change. So this guy is 0. The internal energy is 0. That's the 0 in this one, right? So Q is going to just be, so basically they're just telling you the answer here, but we got to package it, right? Okay, so Q is delta U plus work, okay? So then we set that up, and this is what you're going to do on the IB test, right? Then you'll say Q is equal to 0, because the delta T is 0, right? Plus 1664. By the way, on the website, when I go over these processes initially, as an example, I actually show you how to integrate and get the work done. It's not too hard. It's just the integral of 1 over whatever, right? But anyway, so therefore, Q has to be 1664. So what happens here is that heat flows in, and the heat is directly converted to work. Which, you know, if it took an infinite amount of time, which it would, right? If in order for the temperature to stay exactly constant, you'd have to let this move infinitely slowly so that the temperature never varied. Because an expansion will tend to cool a gas, right? But we don't let it cool. We keep it the same, right? Okay? If we let it go an infinite amount of time, then we can convert the heat that flows in directly into work. Okay? So Q is that, delta U is 0. And the reason for that is that delta T is 0. Okay? And then the work is 1664. I think we've answered every question.